in the advanced light microscopy facility, but actually since recently I am also the Center for Bioimage Analysis. So at EMBL we have this center concept, but this is basically always one person. Okay, then let's start right away. So these are all the players in my or our current big image data approach. So there's the advanced light microscopy facility, and then really big in the middle is the IT services data center, and on the right is the user with a laptop. And this is the most complicated PowerPoint slide with animations that I ever made. And of course now I made a few last minute changes and I broke some of the things, so you have to... But basically the idea is, okay, actually, I heard now from my colleague Tobias that mostly our connections is fast enough that the people really directly save the data on their own group shares, so there's nothing in the light microscopy facility at all. Then the user can, with their laptop, connect to the Linux cluster and actually get a remote access to one cluster node. So I heard from our IT department this is maybe a bit special. And they can actually also get the graphics from there, yeah? So you're on one cluster node and you get like simple graphic, like X11 graphics forwarding, okay? And then there they can, for instance, start my ImageJ big data tools. That's maybe what you refer to. And what that does, it establishes a streaming of the data into ImageJ. That means it only loads on demand the current 3D plane that the person looks at, yeah? So no fancy 3D, just simple slice view. So what you saw, this data set was now drifting a little bit. So the first step that we then, or people do, is you compute a 3D translation correction on the data set. And then actually what happens, this translation is put onto the stream, okay? So we don't recompute any data, we just tell the stream, okay, now make a new stream, but now please load the data applying on the fly the drift correction. The nice thing about this is that you can, within seconds, check if it worked without having to resave 1 terabyte. So I think this is a useful thing. Then, now since the thing is in the middle, you can select the crop. Again, the crop is just put onto the data stream. You get a new data stream and you can look at the cropped thing. Again, you didn't change any data. Everything is within seconds. And then, if you're happy with this crop and with this translation, you can also maybe bin a bit more because the camera had too many or too small pixels. And then finally, save what we now call process data on the file server. And this is by far the slowest step of the whole thing. Okay, yeah, this is where the animation broke. So I wanted to speak about parallelization during the saving. So as we heard before, so one can, actually in our IT infrastructure, I tried it, like if I save TIFF files and I do 10 in parallel, it's really 10 times faster. With 20, you kind of, it's maybe not 20 times faster, but not so much, it kind of leveled off. But you can really do 15 times faster writing if you just do 15 times in parallel. The problem I have right now that for other reasons that I will show quickly, we want to save HDF5 files. Unfortunately, the HDF5 library is not parallel, so I cannot with one Java instance write multiple files, so you would have to do this on the cluster, which would be easy, but again, it's a bit annoying. So, okay, anyway, once we have the process data, then you could put the raw data to tape, and then, like, I think this is more or less exactly what US also has, so people can log into a virtual GPU workstation, and then basically you do all the 3D rendering stuff. Okay, now again, two things highlight at the same time. First, I wanted to make the point that this workflow is basically also used by the electron microscopy facility with some slight modifications in terms of what software they use. But then I want to talk about this process data format. And this is now, again, a bit specific, maybe more for the light microscopy. So what I currently favor here is this model. Yeah? So the idea is, let's say you have a movie with multicolors, okay? So for each channel and time point, we save one HDF5 file and inside a resolution pyramid in an Imaris-compatible way, yeah? Because Imaris has some ideas of how this resolution pyramid should look like. And these files are typically like 1 gigabyte. And then we have made many of these files, and this is a kind of a decent size, yeah? Not too big, not too small, so you can take them home, but it's also, so I think it might kind of make sense. And then for each channel, there's a header HDF5 file, which is basically 0 kilobyte almost. And this is also written in a way that Imaris can read it, and actually Imaris will think this is an Imaris file, okay? And then you can also, on top of this, have another meta file which basically links into all of this. And you can immediately open this again also in IMARIS. And you can also open it in any other software that can reach HDF5. So I think it's pretty good because it's kind of parallel also. You have these files. And yeah, I don't know. Okay, then I wanted to talk a bit more about this part. So how do we do the 3D drift correction computation? So the idea here with this plugin is, first of all, you can select a region of the image that you want to stabilize. So this can, for instance, be if you do developmental biology, maybe only the head of the animal should be stable and the tail should still wiggle or something, right? So you want to say where you want to do it. The other advantage is, again, since it's a data stream, it will only load that part of the image where you were drawing the box, so it's much faster if you only say, I want to register on that small region. And then the other important thing is you can also tell it to, during loading, bin in XY, so that will speed up the computation. And also in Z and T really subsample, so only load every third plane or every third time point. That means, again, you can have, like in this example, it's a factor of 15 that you just load less data. And often for drift correction, that's more than enough. And then this is also why it's actually really pretty fast, so it's really only a few seconds per frame. So there's one professor at the University of Heidelberg, so he had a 2.4 terabyte data set, and he could drift correct this in 15 minutes on the kind of normal computer with this tool. Then to resave the data is another story, okay? But the actual computation is really quick. Okay, then about the segmentation, yeah? So ideally, you just threshold and it's easy, but often it's not, yeah? So for instance, this is an example I'm still fighting with, to be honest. I haven't solved it. So here the person wants to find all the cells and track them, and I think by eye, maybe you can still say you could, I mean, it's really just on the edge where with your brain you think you can still do it. So it's a bit of a challenge. So for these cases, what we also have now is basically, I mean, I don't know, maybe in ImageJ, some of you know this Trainable segmentation plugin. So it's like Elastic, but in Java. So you draw examples, you compute features, and then you train a random forest classifier, and you predict the pixels. So this is basically exactly what you can do here. I just rewrote parts of it to make it big data compatible, so that it only loads every time what it really, really needs. And also you can say, please test it only on a small part of the image. Yeah? And then it's also very fast to train, even if it's a huge data set, because you can just train it on small regions. And then once you're happy, you run it on the whole thing, and then you save it. And with the, okay, and then you could go, for instance, into IMARIS or Arivis again, and then it's easier to segment. So how do we save this processed data? So this, I think, is also kind of cool because of our data model. Simply, this is a new channel. So for each object probability, we have, again, just H5 files. Okay, this is now the pixel probabilities that this was, for instance, a nucleus. And we can simply save a new header file, and then it's immediately attached, and you just load it into, for instance, IMARIS, and you didn't resave anything. Yeah? So you can just attach it basically to the already existing data set, which I think is also good, because you don't have to change any of the other things. Okay, and then I would finally like to show something, and I would like to show it because it is a collaboration with FMI, in fact. So, and at EMBL, actually, I collaborated on with Hernando. And this is a data set, this is a kind of amazing data set that was acquired here of a whole Platina reis animal, which is for EM standards pretty huge. And it took 1.5 months to acquire. And yeah, you can read the numbers, so it's really big. So what Hernando did together with me, we downsampled the whole thing to isotropic 100 nanometer resolution, because that's where he still could see what he wanted to see. So then it's actually only 18 gigabytes, so that's not so bad. And then he used my tool to train 8 different classes. And then after that, and I will show you the results in the next slide, we downsampled it again, that it has light microscopy resolution level, because that's what Hernando wants to register later, the EM to the light microscopy. And then we went into IMARIS to segment the objects and make nice movies. So I will show you now these movies. So this is, first it goes through the whole animal. So the big blobs that will soon come is just lipids, for instance. This is fat that it gets from the mother, that it has something to eat when it's still small. Okay, now if it goes back, you see on the EM data, so the 4 classes that I showed, that is the nuclei, the muscles, then the neuropil, so this is very dense neuron tissue, and then these lipid droplets. And then we just in Imaris did the like the 3D rendering of this. So you see in red the muscles, so they're the legs. Then there's these big neuron things in the middle. Yeah, you can even see the muscle fibers a bit. And then this is what Hernando later needs for the registration, so the nuclei. So I think what's good about this is it's actually, so I asked Hernando, he said he really physically only spent 5 hours doing something on the data set to train it, and the rest, it was just doing stuff on its own. And once you trained the classifier, to get this image, it took now 1 day, but just on a single PC, and it would be extremely trivial to distribute this on a cluster. So I think it's kind of cool, because if you really spend 1 hard day, you can get this in 1 day, actually, with this workflow. It might be not as awesome as the latest super deep convolutional neural network, but it's easy to use, and yeah, just works. So I think it's good. Okay, then I would like to thank, and then this is all the guys from the IT department, so they are really, really helpful, and without them, of course, none of this would have been possible, and I spent almost like every day some time with them. Then Hernando for the EM data, then the SPIM data was from Ashna, and then Ignacio, so he is the developer of the original Trainable segmentation plugin, so I collaborate now with him, and of course my boss, Rainer Peppercock. And yeah, thank you for your attention.